This is the satellite foundational course for GOES-R training on cyclogenesis and potential vorticity concepts. Subject matter experts for this topic were Michael Fulmer and Andrew Orison at NOAA National Weather Service NCEP WPC. My name is Scott and I will be guiding you through this training. Learning objectives are listed on this slide. Because this is a satellite foundational course, you will see ways to relate satellite signatures to potential vorticity. This schematic shows the climatological distribution of potential vorticity. Height is on the y-axis and latitude is on the x-axis, with higher latitudes to the left. The schematic defines the dynamic tropopause as the height of the 1.5 potential vorticity unit, PVU, surface. As would be expected, the dynamic tropopause generally exists at a lower altitude at higher latitudes toward the poles, and at a higher altitude in the tropics. PV units generally increase with height, and because they are related to stability, PV units are largest in the stratosphere where a temperature inversion exists. This schematic illustrates how the transport of an upper tropospheric potential vorticity anomaly can affect lower-level synoptic flow. The circulation around the upper-level anomaly produces vertical motions that deform the isentropic surfaces. The dynamic tropopause, measured by the 1.5 PVU surface, extends to much lower altitudes in the vicinity of the upper tropospheric potential vorticity anomaly. This classic figure from Brian Hoskin's 1985 paper shows how the upper-level potential vorticity anomaly induces a low-level potential vorticity anomaly, and then the two anomalies grow in concert during cyclogenesis when strong upper-level forcing, as shown by the potential vorticity anomaly, is driving the cyclogenesis. There is often a good correspondence between an upper tropospheric potential vorticity anomaly and dry features seen in the water vapor imagery. In this enhancement, blue is relatively warmer temperatures, denoting a drier atmosphere, and white is relatively colder. In this example, NAM40 model fields depict a potential vorticity anomaly at the base of an upper-level low that is moving southeastward over northern Alaska. The dynamic tropopause, denoted as the pressure on the 1.5 PVU surface in red, descended to below the 600 hectopascal pressure level. This system dropped several inches of snow over parts of the Brooks Range of Alaska on the first full day of summer, 21-22 June in 2016. The 9.7 micron ozone band on the GOES 8 through 15 sounder instrument allows for a total column ozone product to be created. And because ozone has higher concentrations in the stratosphere, there is usually a good correlation between a potential vorticity anomaly and high values of total column ozone. Total column ozone is not a baseline product on GOES-R, although ABI does include an ozone band channel at 9.6 microns. Total column ozone is not a baseline product, but high ozone features can be identified nonetheless qualitatively using an Airmass RGB product. In this example of a rapidly intensifying hurricane force low over the North Pacific, the pink shading helps to highlight an area of high ozone associated with a lowering tropopause beneath a potential vorticity anomaly. In the Airmass RGB product, the red component is derived from a difference between two water vapor channels, 6.2 and 7.3 microns. The green component is the difference between the 9.7 and the 10.4 microns, and the blue component is the 6.2 micron channel. A pink value generally contains a lot of red and modest amounts of green and blue. This slide shows the RGB Airmass image from the previous slide on the left. It has been remapped. Component images that go into the RGB composite, shown in the native satellite projection, are on the right. Difference fields are not computed, but there is a toggle between the two bands in native satellite projection used for the red and the green components. The ABI instrument on the GOES-R series will have three water vapor bands: upper level at 6.2 microns, mid-level at 6.9 microns, and lower level at 7.3 microns. This is similar to the AHI instrument on Himawari-8 and 9 satellites, and data from Himawari-8 are shown here. With these three water vapor bands, the identification and tracking of the three-dimensional aspects of potential vorticity anomaly features should be easier. Here is a single image from the animation seen on the previous slide. Red contours show the GFS model pressure of the 2.0 potential vorticity unit surface, denoting the approximate dynamic tropopause, on each of the Himawari-8 water vapor images at 0 UTC on 18 March 2016. A potential vorticity anomaly was moving southward along the western edge of the cloud shield, bringing the height of the dynamic tropopause down to the 450 hectopascal pressure level. Note the well-defined signature of subsidence, warming and drying, behind the potential vorticity anomaly, and the signature of ascent, cloudiness, ahead of it, on the upper level, the 6.2 micron, and mid-level 6.9 micron water vapor images. This drying is a common feature with potential vorticity signatures and is frequently visible in both single channels on the AHI and ABI, and also in RGBs that include water vapor channels. This animation of Himawari-8 water vapor imagery, with 6 hourly GFS analysis contours of the pressure of the 2.0 potential vorticity unit surface in red. This allows you to follow the upper-level potential vorticity anomaly as the surface low intensified to produce storm force winds during the 17 to 19 March 2016 period. Note the drying and warming behind the potential vorticity anomaly and the cooling and moistening ahead of it. You will frequently see this relationship. This slide should remind you of what you just learned. Potential vorticity anomalies that induce cyclogenesis can be inferred from signatures in the water vapor imagery, especially the upper level and mid-level channels on ABI and AHI, 6.2 and 6.9 microns. Overlay model fields near the dynamic tropopause, 1.5 or 2 potential vorticity units, to reassure yourself that features in the water vapor imagery are indeed potential vorticity anomalies. The Airmass RGB product can also provide useful information. You can find additional information and examples about water vapor imagery, the Airmass RGB product, and potential vorticity anomaly cases at the links on this slide. This concludes the Satellite Foundational course for GOES-R on cyclogenesis, potential vorticity concepts. Thanks for listening.